This video is about section 1.2, in which we discuss a tool called slope fields. In the previous section, section 1.1, we indicated that our goal will be to find the solution of a differential equation. The solution could take one of two forms. We could be interested in finding a general solution, which is actually an infinite family of functions that satisfy the differential equation, or we could be looking for what our author calls an actual solution, in the case where we're provided with initial conditions. And just as a quick reminder, our author calls a differential equation plus initial conditions an initial value problem, or sometimes he abbreviates it IVP. So our goal for the most part this semester will be to discuss different techniques for how to solve differential equations, how to find solutions. But before we get to that topic, in this section we're going to discuss a tool called slope fields. Slope fields are a tool that will help us visualize properties of solutions to our differential equation in the case that our differential equation is first order. If we have a differential equation that's not first order, we cannot apply this tool of a slope field. And while a slope field does not provide a solution to our differential equation, it does allow us to glean important information about solutions nevertheless. To demonstrate how a slope field works, let's take a look at this first example. The differential equation we're provided with is y prime equals y plus 1 times the quantity y minus x squared minus 1. The fundamental idea that drives the construction of a slope field is that a y prime term, a first derivative, indicates the slope of the solutions. As such, I can manipulate my first order differential equation to identify more specific information about slopes of solutions. The first step I typically take is to set y prime, set the first derivative, equal to 0. You'll recall that when y prime equals 0, a function has a horizontal tangent, or sometimes we say a function levels out. So if I can identify the point or points at which y prime equals 0, that will indicate where on my solutions there is a horizontal tangent. In this particular case, when I set y prime equal to 0, I have a simple expression where two terms are multiplied to give me 0, so I can solve by setting them individually equal to 0. I'll do a couple quick steps of simplification, which indicates that along the line y equals negative 1, and also along the parabola y equals x squared plus 1, along all of those points in the plane, solutions to this differential equation will have a horizontal tangent. That is, they'll have a slope of 0. Slope field is simply a representation of the properties that I've gathered from my differential equation. In this case, we've indicated that we have two places, two curves, where I know that solutions to my differential equation will have slopes of 0. So what I want to try to do on a graph is try to display those properties. First, let me display the fact that along the line y equals negative 1, my solutions will have a slope of 0. That means that the line y equals negative 1, which is a perfectly flat line, will be one of the solutions to my differential equation. Similarly, I know that along the line along the curve y equals x squared plus 1, I'll also have horizontal tangents. Unfortunately, I can't simply draw the curve y equals x squared plus 1 because that curve doesn't have horizontal tangents. So what I'll do instead is I will sketch the curve y equals x squared plus 1 just to have some sense of its shape, but then along that curve I will indicate on my graph that the function should have horizontal tangents. Here I've done my best to indicate that along the curve y equals x squared plus 1, the functions that are solutions to this differential equation will have flat horizontal tangents. So if a function, which is a solution to this differential equation, passes through one of these points, it will level out at that point. Those are the only two curves along which solutions have horizontal tangents. So whatever the solutions of my differential equation look like, and again we're talking about the general solution, so there are infinitely many functions that I'm trying to describe here. Whatever those solutions look like, there's nowhere else that they will quote-unquote level out. There's nowhere else where they'll have a horizontal tangent. For reference, let me call those regions region 1, down here below y equals negative 1, region 2, sort of in between these two curves, and then region 3 is above the curve y equals x squared plus 1. Now let me investigate the properties of my differential equation on each of these regions individually. In region 1, I know that the y values are below -1, and I also know that the y values are less than x squared plus 1. There's a little typo. Referencing my original differential equation, if y is less than -1, then that means that this term, y plus 1, will be negative. Similarly, if I know that y is less than x squared plus 1, then I know that this term will also be negative. So in my overall differential equation, I'll have two factors on the right that are both negative. When those are multiplied together, that yields a positive value. So in region 1, I know that my derivative, y prime, will be positive. That is to say that I know that solutions that live down here in region 1 are always increasing. I know that they won't increase to the extent that they'll actually break through this threshold, but all of the solutions down here in region 1 will be increasing. I'm going to take a second to do my best to try to represent that on the graph. I've drawn a few potential functions that have this property that since they're in region 1, they would be increasing up to y equals -1. I'll follow a similar process for region number 2. Based on the properties of the inequality, I can determine that in region 2, solutions are all decreasing. Now, there's a couple different types of solutions here. I expect that many of the solutions over here in this region, this part of region 2, will simply decrease. So if I have an initial condition which indicates that my function starts somewhere over here, these solutions will simply decrease and approach y equals -1 as x grows without bound. I have a few solutions though such that when they decrease, they will approach this horizontal tangent, and then they'll pass over that sort of boundary there, and then they'll enter into region 3. So I could potentially have solutions that decrease. I know that as long as they're in region 2, the solutions must decrease. But as they approach the curve, y equals x squared plus 1, they will approach a slope of 0. Similarly, as functions exit region 3, I know that if they have a slope of 0, they must, as they exit region 3, start to decrease. So I know that my solutions that exit region 3 must decrease and look something like this. This sketch is pretty rough. I'm not doing a great job providing really accurate drawings of these potential curves, but I am just trying to get a sense of the general behavior of what these solutions would be. Let me repeat the process for region 3. These brief calculations indicate that in region 3, the derivative will be positive. So any functions that exist in region 3 will be increasing throughout region 3. So that means that if a function approaches on the left from region 2, levels out, has a horizontal tangent, that function will then, while it's within region 3, will be increasing. As it approaches this sort of right-hand side of region 3, we know that the slope will approach 0, and as it crosses that boundary defined by the curve y equals x squared plus 1, it will have a slope of exactly 0. So these solutions will increase until they reach this right-hand boundary, and then they will decrease. Again, this is a very rough representation of what these solutions look like. But I'm trying to get a general qualitative sense of what solutions to this differential equation look like. So this is a very approximate view of what a slope field would allow us to determine about my differential equation. While this does feel a little rough, one thing I can say definitively is that for every solution of this differential equation, no matter what my initial condition is, it looks like all solutions will eventually tend to -1. Remember, these solutions out here are always decreasing, and so they'll always decrease and approach the line y equals -1. So that's one definitive conclusion I can make about the solutions of this differential equation. I can also note that there will be some differential equations, such as those whose initial conditions place them down here in region 1, which do not have any critical points. Similarly, there will be some solutions in region 2 that do not have any critical points, but I know that there are some solutions such as those that pass through region 3, which will have two critical points, a local minimum and a local maximum. So even though I don't know exactly what expression for solutions of this differential equation are, I can still draw some properties, draw some conclusions about those solutions. If we scroll to the next page of the notes, we see a computer-generated version of the same slope field that we just sketched out. This computer-generated version is much neater than mine, but we see some of the same general properties. We see that all solutions will decrease and eventually approach y equal -1. Also, if we look carefully, we can see the general structure of the curve y equals x squared plus 1, where these solutions have horizontal tangents. And we do in fact see some solutions that decrease, cross over that curve, that boundary y equals x squared plus 1, increase, and then eventually decrease and continue decreasing until they approach y equals -1. If you're interested in trying to generate some slope fields of your own, this is the website that I use to generate this particular slope field. I want to look at one more example, and before we do, I just want to sort of summarize the process of how we would generate a slope field in general. So in the middle of this second page of notes, I've indicated 3 strategies for constructing a slope field. And the idea is to work through as many of these steps as necessary until you've generated sufficient information to be able to draw some interesting conclusions about your solutions. So the first step is to set y prime equal to 0. This yields points at which the solutions have horizontal tangents. And in the previous example, this was the only step that we took. And once we had completed this step, we had enough information to sketch some qualitative representations of what solutions to our differential equation would look like. An optional second step is to plug in 0 for x and or y. This gives us explicit information about the slopes along the y and or x axes respectively. And then a third step is to plug in other convenient constant values for x and or y, and this gives us information about the slope values along lines determined by those chosen x and y values. To demonstrate, let's look at example 1. In example 1, I have 3 differential equations and 3 slope fields. My goal is to match the slope field to the differential equation using any of the strategies that will help that were just identified. Let's consider the differential equation in part A. Y prime equals -1 minus 2y. As indicated above, my first strategy is to set y prime equal to 0. This indicates that I will have horizontal tangents for solutions along the line y equals -1/2. As with my previous one, this might be enough information to get a general sense of what my slope field looks like. But let me follow at least one more of the steps described above. Let me try setting y equal to 0. This indicates that when y equals 0, y prime will be -1. Y equals 0 corresponds to the x-axis. So this tells me that if I look at the x-axis of my slope field, the slopes of all of the little hash marks should all have a slope of -1. It's pretty clear to me that this third slope field meets these 2 descriptions. Notice that along y equals -1/2, I have horizontal tangents. My tangents aren't perfectly horizontal in the picture. That's just based on the grid size that was chosen to calculate this computer-generated image. And then along the x-axis, everywhere along the x-axis, I've got negative slopes, and those slopes are pretty much exactly y equals -1. So I think this slope field corresponds to our first differential equation. Let's take a look at our second differential equation, part B. Y prime equals -2 plus x minus y. Let's again start by setting y prime equal to 0. This indicates that solutions will have horizontal tangents along the line y equals x minus 2. So I'm going to look at my graph and try to identify the curve y equals x minus 2, and along that curve I'm looking for horizontal tangents. Let's, in this example again, follow the second step of plugging in a convenient value for y or for x. Just to change our process a little bit, let's try setting x equal to 0. This indicates that slopes along the y-axis will be given by the expression -2 minus y. I'm not going to try to calculate specific slope values. I just want to think about generally, qualitatively, what is this telling me? This tells me that the slopes, if I consider positive y values, so if I looked along the positive y-axis, as the y values increase, I expect my slope to get more and more negative. So in this expression here, if y is positive, then the overall expression is going to be negative. And as y gets larger, that corresponds to going higher and higher up the y-axis, then my slope should get steeper and steeper and negative, even more and more negative. Hopefully it's clear that this first slope field satisfies those properties. First, I see horizontal tangents along a line that I could recognize as y equals x minus 2. Then we also indicated that if we looked at positive y values, we expect the slopes to all be negative, and as we increase our y value, as I go farther and farther up the y-axis, I expect the slopes to get steeper and steeper negatively, and they all do. It should be clear that this third one, by process of elimination, corresponds to our third differential equation. But let me work out some steps just to verify that. Several calculations based on this third differential equation. First, I set y prime equal to 0. And again, those are that indicates the location of the horizontal tangents on my slope field. So it looks like those will occur along the curve y equals negative 2x. Next, I set y equal to 0. And in this differential equation, if y equals 0, I'll have 0 in the denominator. So that indicates that I'll have undefined slopes, essentially slopes that will be perfectly vertical. I could further set x equal to 0. This indicates what the slopes will be along the y-axis. And this says that all along the y-axis, slopes should be constant at negative 1/2. And then just to take it a step further and demonstrate that third strategy, I chose setting y equal to x. Y equal to x is, of course, the curve that goes straight through the origin, has a slope of exactly 1. And by setting y equal to x and simplifying, that'll allow me to identify what slopes should be along that curve. As I mentioned, we've already used the process of elimination to determine that this slope field does in fact correspond to this differential equation. But let's just verify that all of these properties are held. First of all, we should see horizontal tangents along the line y equals negative 2x. And if I imagine a line at y equals negative 2x, I do in fact see those horizontal tangents where I would expect them. When y equals 0, that is along the x-axis, we said we should expect slopes that are perfectly vertical. And that is more or less true. Again, this image is a computer generation of the actual slope field. So it's setting a lattice, and maybe these slopes aren't perfectly vertical, but those certainly seem to agree with that general property. So maybe this computer-generated image isn't perfectly representative of what the slopes should be, but we get a very clear approximation in this case. Similarly, when x equals 0, those are points along the y-axis. We expect the slopes to all be negative 1/2. They appear to be. The origin is acting a little strange, but that's okay because that's where y equals 0 also. So we expect that slope to be undefined, and so I'm not surprised that it would act a little strange. Lastly, along the line y equals x, we should see slopes, constant slopes of negative 3/2. And if we imagine looking along the line y equals x, all of these tick marks, again with the exception of the origin, do appear to have the same slope, and that is a rather negative slope, so it would be reasonable to assume that that slope is negative 3/2. So this last example demonstrates some techniques that you can use to try to generate properties of a slope field, or in this case, generate enough properties to be able to identify, to match up which slope field corresponds to your differential equation.